Let's talk through how you would apply the concept of a system to an example problem with multiple moving objects. And we return to our herpetologist pushing and accelerating this crate of asps and this crate of boas across the floor. Suppose that we are given the following information: the mass of the crate of asps, the mass of the crate of boas, the coefficient of kinetic friction between this crate and the floor, the coefficient of kinetic friction between this crate and the floor, and also the force on A due to H. That's how hard the herpetologist is pushing onto the crate of asps here. So if we're given that information, we are asked to determine the following: the acceleration of crate B across the floor, and also the force on B due to A. How hard is this crate A pushing on crate B? We're going to decide along the way which objects to include in our system, but our general problem-solving strategy for this dynamics problem remains mostly unchanged. We'll still start with a free-body diagram for each moving object, and we'll choose our axes, and then at that point, when it comes time to use Newton's second law, then we'll decide whether to define a system. So let's start with the FBDs. We've drawn these before. So for each moving object, the herpetologist, the crate, and the other crate, we've got the full set of free body diagrams. Triple A, there's our set of axes right there. We know that we're accelerating to the right, so we'll align our axes with that acceleration. And now we should consider whether to define a system here. So we want to know which objects to include in our system. And so we'll need to consider what we know about all these forces here. Remember, the given information is this. So with that given info, let's consider for a moment the vertical direction of motion, the y direction here. Here's a few considerations. If we're going to sum the y components on the herpetologist here, we've got the normal force and the force of gravity. We know those sum to 0, but we were not given the herpetologist's mass, so there's not much more we can say there. However, here for crate A, we can sum the forces in the y direction, and since we know the crate's mass, ma, we can also then say something about the force of kinetic friction on the crate. Since we know that kinetic friction can always be found from this formula, since we're given the coefficient of kinetic friction between the crate A and the ground, and we know the mass of crate A, we now know that we can solve for the force of kinetic friction in terms of our givens on crate A. And similar argument for crate B over here. We can solve for the force of kinetic friction on B in terms of our givens. So my point here is that we can look at these free body diagrams and recognize that with our given information, we can solve for this normal force, this force of gravity, and that force of friction, this normal force, that force of gravity, and that force of friction. So we can consider all of these forces, those 6 forces there, to be givens at this point. We can solve for any one of those should we choose. However, over here with the herpetologist, we don't have enough given information at the moment to find any of these 3 forces. So there's a lot more unknowns in this free body diagram. And recognizing that, it suggests that maybe when we define our system, we shouldn't include the herpetologist in it because there's just so much unknown about this FBD. Maybe we should focus our system here on the 2 forces, on the 2 objects where we know more. Looking at these 2 free body diagrams, here is the force applied on H by the herpetologist. That's given to us. So really, the only 2 unknown forces here are how hard the 2 crates are pushing on each other, that internal force pair right there. So now I feel like I want to define these 2 as my system because there's really a minimum of unknown information here. All right, so let's now shift our focus, sort of push the herpetologist out of the picture and consider just these 2 crates to be our system. And here's the free body diagrams for those 2 crates right there. And once again, the only unknowns here are the force on B due to A and the force on A due to B. That's an internal equal and opposite Newton's third law force pair This crate's pushing on that one. B is pushing back on it. So we've got an internal force pair right here. Okay, the next thing that we might want to notice is that since A and B are in contact with each other and they're moving together, they're going to be moving as one. That's an important consideration. In fact, anytime we've got, say, a system of objects, like, say, this school of 3 fish here, that sort of move together, all 3 fish sort of have the same velocity and acceleration all the time. When you've got a scenario like that, a system where all the objects move as one, if the objects in your system are moving as one, so here's your 3 objects, A, B, and C, like those 3 fish, and they're the center of mass of that system. If they're moving as one, then they all have the same acceleration at every instant, and the center of mass is the same acceleration as well, and they all have the same velocity at any instant. So moving as one means they have the same accelerations and same velocities. Recognizing that, it leads us to our strategy for a scenario like this. We do want to find the acceleration of the crate, but we also want to find that internal force, the force on B due to A. That's one of the things we're trying to determine. So in a situation like this, if you want to solve for an internal force and the objects in your system are moving as one, like the fish here, our crates are moving as one. So if that's your scenario, then we have a 2-step process. Step 1, first we're going to apply Newton's second law for a system, this equation, and solve for the acceleration of the center of mass. Then we'll come to step 2. So let's do step 1 first. Newton's second law for a system. We're going to get the acceleration of the center of mass by just summing the external forces divided by the mass of the system. So what you would write down is this statement here, state that equation, then maybe note that the mass of your system can be expressed as ma plus mb, and now sum the external forces by looking at these 2 free body diagrams. We're just looking at the x direction here. So on this FBD, I've got 2 x forces, but that's an internal force. Here I've got 3 x direction forces, but that again is an internal force right there. So our external forces are the force on A due to H, this force of kinetic friction, and that force of kinetic friction. Sum just those 3 external forces and divide by the total mass of our system of these 2 crates. And look, at this point, basically, we have now solved for the acceleration of the system. This is given, and we know we can express those 2 forces of friction in terms of our givens. So right there, by using the systems approach, without worrying about this internal force at all, we have already solved for the acceleration of our system. That's step 1. Now, step 2, once you've solved for the acceleration of the center of mass, now use Newton's second law for a single object to solve for that internal force we want to find. So now we can go back and pick either this object or that one, this one or that one, and do Newton's second law for just one of the objects to find the internal force. So we could focus on just this object and use N2L to find that force. Or since we know that these are equal and opposite, we could also focus on this object and use N2L for this object to solve for that internal force. I guess we have another decision to make. Do we do N2L for crate B or N2L for crate A? How do you decide? A good guideline is, which free body diagram is simpler? This one has 2 forces in the horizontal direction. This one has 1, 2, 3 forces in the horizontal direction. So there's just more going on over here. It's more involved. So given the choice, I'm going to choose crate B. Let's do Newton's second law just for crate B right here, since it's got the simpler free body diagram. Okay, so in step 2, now we're getting the internal force. We have to do Newton's second law for a single object to get an internal force, because if we do N2L for a system, the internal forces don't show up in this equation at all, so we can't find an internal force from this approach. We have to go back to good old Newton's second law for a single object, where we sum all the forces, including the external ones. So here, Newton's second law for crate B, sum all the forces on crate B. That means in the x direction, FBA minus this force of friction. There we go. and then we're going to rearrange this to solve for the force on B due to A. So just do a little algebra, multiply both sides by MB, then I'm going to add FFKB over here, and now we've got our result. The force on B due to A, that's our internal force, can be expressed as this sum over here. And that's basically our answer because we know all of these things in terms of our givens. Do you see why? Let's go back here. This expression for acceleration of the center of mass, if we plug in our given information, we know FAH, and then we showed on the previous page that we can express these two forces of friction in terms of these combinations of variables here. So this would be like your final answer in terms of just the given variables. That's our acceleration of the system. And then down here, for the internal force, how hard A pushes on B, well, we just take the mass B times this acceleration here. Plug that in right there. Plug that whole expression in here. That's why this is step one. Find this acceleration and plug this whole thing into there because our objects are moving as one. So the acceleration of the center of mass is equal to the acceleration of B. So we take this whole expression for the acceleration of A, plug that in here, and then have mb times all this plus, and this force of friction on B we can express in terms of our givens here. So this would be our final answer, this combination of variables, just in terms of givens for that internal force. And that is our two-step process for handling a scenario like this.